Hello everyone, welcome to another video in the Morphometric analysis series. So in this video we will discuss another morphometric parameter which is called steepness index. First we will develop the theoretical background and will understand the theory of this particular morphometric parameter and where it can be utilized. And then we will go to QGIS to learn step-by-step methodology to calculate the related parameters. Okay, so let's begin. So let's learn how we can define the steepness index. So basically the topographic data from any river channel shows a pattern where steepness of the channel can be described, right? Steepness, and that it can be defined using a mathematical formula where you see the relationship between the slope of the channel and the area of the land that drains into the channel. Okay, so basically these two parameters are related by this mathematical formula where your S is the slope of the channel and A is the area of land draining into the channel. Okay, so this area, it serves as a proxy for local discharge. This Ks is the steepness index, a constant value that affects how steep the channel is. Okay, so this tells us that how steep the channel is. And theta is the concavity index. And what is concavity? It is the rate of change of local channel slope as a function of increasing drainage area. Okay, so I hope these parameters are clear. So when you look at the unperturbed concave up river profile, okay, the river profile which is not disturbed by any external factors or is in equilibrium, okay, so such sort of profile we saw in the hypsometric curve analysis where these profiles develop in the late stage or in old or monadnock stage of erosion. Such unperturbed concave up river profile shows a consistent pattern of steepness in relation to drainage area along their length. If you see here, you see there is a consistent pattern. There is no break that we can find in the steepness. This is log slope and log area map. Okay. Now, if you see a perturbed or disturbed longitudinal river profile, it will have a slope break. Okay, such sort of profile will have a slope break and such slope breaks are called Knickpoints. Okay, so this tells us that in nature, different sections of a single river, you see this is a single river, may have varying steepness, right? It may have varying steepness and concavity values. So these variations actually we require to understand the tectonic activity in a landscape. Okay. So if you plot the log slope and log area of such profiles, you will see that there is sudden increase in the slope of the river, which is manifested in the form of change in steepness or increase in the steepness at a particular point. And such points are called Knickpoints. So basically a Knickpoint is a sudden break or increase in the slope in the river long profile and is represented by an increase in the steepness, right? Here you see the steepness increases. So there can be different reasons for the presence of such Knickpoints, and the factors can be the presence of different lithology. Maybe you say at this point that there is a change in a lithology, maybe softer to harder or harder to softer. Okay, or it can be the response of a river to some climatic event or the response of a river to some tectonic uplift. So steepness index, okay, is fine when you want to calculate the parameter just for a single channel. However, if you are comparing the steepness among the channels of different sizes and different regions, with different concavity value, a normalized steepness index is required. Okay, so where it is calculated with the theta reference value of 0.45, and it is useful for easy comparison with rivers regionally. Okay, so normalizing the steepness is important because it allows for the comparison of river steepness across different regions and river sizes. Tectonic insights, it helps us identify areas with higher tectonic activity, as regions with faster uplift often have high KSN. What is KSN? Normalized steepness index values. And also it gives us the simplification. It simplifies the analysis by reducing the influence of drainage area size on the steepness measurement. By using the normalized steepness index with a theta reference value of 0.45, it becomes easy for us to compare the rivers of different drainage area sizes. Okay, so in our analysis we are going to use the theta reference. So basically the changes in steepness indicate changing rock uplift rate along a long river profile, and of course it affects the concavity of the river profile spatially and temporally. Right, so you can see from this relationship between steepness index with rock uplift and erodibility is that the steepness index, it increases it increases with the uplift rate and decreases with erodibility, right? So where your K is the erodibility, it is primarily related to lithology, climate and hydrology, because these are the factors that affects the erodibility and how efficiently a rock can be eroded, right? So these are the factors that affect the rock erodibility. And U is the tectonic uplift rate. So more the tectonic uplift rate, more will be the steepness. So based on this, we can say that there are many factors that prevail in the nature and that creates a complex system of fluvial environment and indirectly or indirectly influences the river steepness. For example, the river adjustments in channel width or sinuosity, sediment load, orographic enhancement of precipitation, varying geological setting, climatic factors, and substrate rock properties, they all affect the bedrock river channel steepness, and that is reflected in the calculation of steepness index. Okay, so basically bedrock river channel steepness index can be used to infer relative differences in rock uplift rate across a landscape given uniform lithology and climatic forcing. Okay, so these are some of the assumptions or some of the things that we have to take care of while interpreting our results. So based on our understanding of this particular morphometric parameter, we can say that rapidly uplifting hard rock requires the steepest channel slopes, right? Steepest channel slopes to erode at a pace that is comparable to the rest of the river system. So therefore, we expect Knickpoints or steep zones in rivers to occur where hard rocks are hard or tectonic uplift is fast, right? And if we talk about the temporal changes or the changes with time in climate and tectonics, that of course complicate these relationships, but identifying these changes can provide us the invaluable information for tectonic analysis. So therefore, stream profile data, okay, that we are going to extract using QGIS becomes very important and is helpful in extracting regional tectonic information or the information on the factors affecting the landscape evolution of the area. And the methodology for this process will be discussed in detail. So for this analysis, as we saw in the formula, we need to estimate the slope, length and elevation and uh, drainage basin area basically. And in the upcoming video, I will explain the QGIS method to gather and calculate these parameters. So in this slide I have given the literature that I have taken help for creating this presentation, creating this video for understanding the steepness index. You can go through these both these papers. They are really nice and easy to understand research papers that you can refer for better understanding of the steepness index. And if you had any problem in understanding this theoretical part, do write in the chat box so that I can give you maybe a better method to understand this parameter. So thank you for your attention. So now you may go to the next video to see the step-by-step tutorial or step-by-step QGIS method to calculate this parameter. Thank you.